Yeah, welcome to my talk about TPMs and why they are no silver bullet, especially on embedded devices. Just very briefly about me. My name is David. I work at Gstir GmbH. Actually, I'm one of the co-owners, so to say, and I'm responsible for all things security, essentially. We do a lot of security audits, so we look at the source code of people who have products in all ranges of things. We also do engineering and consulting, especially everything around Linux and embedded systems and security. So that really sums it up to go to TPMs. So the reason I'm doing this talk basically is we are approached from customers in embedded security for various reasons and consult them on aspects of Linux and security. And more, recently TPMs come up, especially with regulations and stuff like the CRA, but other regulations that require a certain amount of security from your product or device. People often come to us and say, yeah, but we have a TPM. We can solve it with that, right? And the answer then is, well, it depends. So this talk is intended to give you a bit of an overview of what things you have to consider when you use a TPM and what things a TPM will not solve for you, especially when it's on an embedded device. So very briefly, TPM, I think it should be quite familiar because they're around for a long time now. They were on laptops and PCs. There was a big, initially there was a big fuss about them to invade your privacy and being used to prevent you from running Linux on your computer. But nowadays we do have them. They are somewhat usable, and they are in basically every laptop which is running Windows, because Windows 11 started requiring them. So it's a hard requirement from Windows 11 onwards. But we also have them in Linux, right? So systemd has support for TPM-backed disk encryption. And it's quite nice. It's really usable. It works out of the box, and they have done a good job of integrating it. A TPM is basically a dedicated security chip which lives on your mainboard somewhere and which is connected to the rest of your system, especially your CPU, via some bus. There are a bunch of them which TPM support, depending on which chip you use. But they are rather seldomly used on embedded systems, at least from what I've seen. The latest specification is the TPM 2.0, which is quite good because while they still have the old broken cryptography in there, they also support newer, more recent state-of-the-art cryptography like elliptic curves. They still have RSA. You can do HMAX. They have like recent hash functions, not like SHA-1 only. You have AES, like symmetric crypto. You have a random number generator, which is cryptographically secure, so it can give you good random numbers to generate, for example, keys. They have TPM has multiple. I won't go into all the details, but TPM has multiple key hierarchies where you can create new keys, which are then protected by one of those root keys. There are 4. From what I'm aware of, there's the platform, the storage, endorsement, and null key. Each has its own purpose and use, so you can't use them for everything. If you want to have a headache, go read the specification. It's horrible. And TPMs can do authorization, and that's important because the TPM is a security chip, right? So you want to make sure that not everybody can use your keys in there. Also very, very prominent are platform configuration registers, which are used, as we will see, for things like measure boot. And it has a small amount of persistent storage where you can store stuff on it, but you don't need to always. Let's just go through 3 of the main uses for TPMs, which we do use nowadays. I mean, they're probably intended for more, but the main uses are these. Yeah, we have secret storage. I mean, that's the whole thing about disk encryption, right? You have an encryption key, which is usually your password, but you don't want to type in your password all the time. So you use a TPM to store that key. And the TPM gives you the ability to simply have that chip on your mainboard, and when your system boots up, it will get the plaintext key out of it and unlock your disk for you. You can also combine that with a low entropy password. This is a PIN, basically, so you don't have to type your 20 characters or more long password, and just can type a few numbers, and the TPM will then unlock if those numbers match. You can also use them for other things, like storing your private keys for TLS, VPN, or SSH, or something like that. So there's a bunch of uses which you can do, and some of them also make, of course, sense for embedded systems, right? So if I have an embedded system which connects to some cloud backend, then it's nice to have a private key which I can store in the TPM, and which will protect that for me, and I don't have to come up with a custom solution. As I said, they have TPM has key hierarchies. All you need to know at this level, which we're talking about here, is it's basically an internal key to the TPM, and the TPM makes sure that those private keys stay inside of the TPM. It's really hard to get them out. What the TPM will, however, allow you is to use them, right? So you can use them to sign stuff, to encrypt stuff, or decrypt stuff. We can also give the TPM a bunch of data and have the TPM what's called binding, which is basically encrypting it for us and authenticating, of course, which is what this encryption basically does. We give them our data, which is the secret. We have the TPM bind it, so it uses an internal key to encrypt and authenticate it, and it will give us back a blob, which you can then use and store, let's say, in the case of the encrypt in the LUKS metadata header. And then when we boot up next time, we will go to the disk, read that part, give the blob to the TPM, and if everything else, authentication, matches, the TPM will decrypt it and give us back the plain text. So as I said, there's small internal storage, which we could also use, and which we sometimes need to use, but to not be limited, or for scalability reasons, you can also store everything outside. The second part is measured boot, which not to be confused with verified boot or secure boot, because the terms are a bit fuzzy here. So measured boot is something different than verified boot. Verified boot, probably most of you, if you're doing something with embedded, know, which is when you sign your bootloader, every stage of your boot process, and the previous stage verifies the signature on the next stage before it hands over control. With measured boot, we do take measurements of all our boot stages or components, which we will then send to the TPM, which will use them to extend PCR registers, which are essentially hash values. And the nice thing about those is that you cannot really modify them directly from the outside. The TPM will update them according to the measurements it gets, but it will not allow you to write a specific hash value in there. So you have to reproduce the measurements. And you can also update PCR values by simply sending new measurements, and the TPM will update the respective PCR hash by really extending it, which is taking the previous hash value, adding your stuff which you measured into it, and then producing a new hash value. So it's hard to tamper with them, let's say. It's also nice because we can combine that, so to finish up measured boot, with all those PCR hashes produced at the end, we can verify by reading those hashes back what stage our boot process is. And we can detect if one of those PCR values does not match a previous value we know or we expect, then we know something went wrong and something was tampered with. We can also combine it with secure storage by simply telling the TPM, you only unlock this key if the PCR values of those PCR registers match what we currently have or what I want you to have. It is also something systemd does, right? So with systemd, I think it's script and roll. You can just specify a bunch of PCR registers which you want to include the TPM in unlocking. And the third most common use case is attestation, or especially remote attestation, which is basically you want to ensure, before you talk to some device, you want to ensure that it's within a specific state. And for that, we use what we just discussed. We use PCR registers. We use the cryptography parts inside of the TPM. And the TPM provides us the ability to really get a cryptographic quote on the state of the machine. So you can then identify the machine and also identify and ensure that it's in a secure state before doing anything sensitive with it. It involves a different key, that's the attestation key, which for historic reasons and privacy reasons you will first have to create, and then you have to verify if that's really the key that TPM generated. So there's a whole bunch of things involved there to make sure you're talking to the right TPM, and that's correct. There's a great talk by Matthew Garrett about that from, I think it's 2022 or something like that, which I've linked here, which goes into a bunch of the basics with remote attestation, if you're interested in that. Yeah, now let's talk about embedded devices and TPMs. As I said, it's not really that common, but it's possible. There's been a lot of work in certain areas like bootloaders and other parts, which make it possible to use a TPM on an ARM-based system, which is the most common one for embedded systems. What you do need, or what the main difference to the standard PC or notebook is, you need to handle all the UEFI stuff somehow. The cool thing is U-Boot, and I think other bootloaders, but mainly U-Boot, which is what I know, implements UEFI, so you can run UEFI applications in there, and it acts basically as that. You will at that stage, however, also need a verified boot for the initial part, right? You have some boot ROM on your device, which then goes hands of control to your bootloader, and that part is not protected by, or cannot be protected by a TPM, because it's not initialized at that stage. So you can do that. There's probably vendor-specific solutions for that, but you will need to handle that yourself. There's no out-of-the-box solution. And there's also the optional part which you can do. You do not need the real physical TPM chip. You can have like a firmware-based TPM. And there's already really existing support for that. You can use Opti with an ARM trust zone. And there's a FTPM trusted application, which I think is now already really maintained or hosted at the Opti GitHub. So you can use that and run basically a firmware TPM within Opti, within your trust zone. Manuel Trout did a nice talk on that in 2024. Full disclosure, we did review some parts of that, what he did there. The main difference when you talk about security and embedded devices with TPMs is the threat model, because when you look at it, there's some major differences from a threat model perspective. With my standard laptop, I'm the user who's using that. I want my data protected from there, and I most of the time have the laptop with me, right? With an embedded device, especially if it's a consumer product which you sell in masses, you don't have that. The point at which somebody buys your product, they basically own it and they can do whatever they want with it. It's also that most of the time, it's not the customer who buys the product who wants to protect data. It's you as the vendor who wants to protect, let's say, your IP and everything on the system. So you want to make sure that as a vendor, the device is sane, but the user might not have that same intention. There's also, of course, no physical presence. You cannot have the user enter a PIN, because first of all, you don't want the user to know that PIN. You just want the device to be plugged in and boot up. Yeah. The exposure, as I said, is trivial. User is always the potential attacker in this case. Also, the device is often up 24/7. So let's say for an IoT sensor, that thing is running 24/7 because it needs to measure data and produce sensor data. That we will go back to that because that makes a difference depending on how you use the TPM. Yeah, as I said, the environment is also a bit more hostile. Everybody, if they buy your product, they can do whatever they want with it. They can open the enclosure, they can look inside, they can go and solder stuff on there if they want to. And they can watch the whole thing during normal operation. With a PC like that, I usually don't have that because the one operating the PC, that's me. And if somebody else boots it up, I expect that to not be working, so at least that they don't get to my data and they don't get that far. On the upside, however, an embedded device always has or most of the time has a more tailored single use case. So it's not like a broad use case and you don't have to support everything. So it might be a bit easier to lock down and implement certain measures. Yeah. Now let's go into some of the common threats you have on embedded devices combined with TPMs and pitfalls. The first, as an answer to, well, I have a TPM and it will solve that for me, is, TPM and cryptography on TPMs is slow, right? So it's not fast enough. It's a microchip. It's not really that fast. So it will not handle high volume data. So it will not handle like your whole TLS connection or VPN connection. It will do the handshake part. It will handle your private key, but it will not handle the whole volume. Also, disk encryption does not work. You cannot push the whole data you write to disk through the TPM. I mean, Apple, on the other hand, implemented something like that, but they didn't use a TPM, so they produced their own chip, which is fast enough to handle this with, it's called Secure Enclave, I think. Yeah, so with that limitation in mind, we do have to, for performance stuff, we do have to get the keys or the secret data back out of the TPM into our main CPU and into our memory. So a private key for my disk, which I want to encrypt, will live in main memory. So I have to use other measures to protect it. The TPM will not help me there at all. So that's also a case where you want stuff like measured boot, where you want to have measured boot and ideally also verified boot, and you also want to have other measures implemented. Also, I mean, the prime example here is cold boot attacks, right? So if it's in main memory, somebody might be able to extract it from there, and they don't have to attack the TPM at all. About additional measures, the whole thing is runtime integrity protection. So a TPM will verify with measured boot, verify your boot process, but after everything is booted, the TPM will not see what happens afterwards, right? So any modification that happens after that, so let's say you have like a vulnerable network process and somebody manages to execute code via that, TPM will usually not notice that, unless they persist something to disk, which in fact modifies your any boot stage. And then the PCI register hashes will change. So in that case, you will need additional measures again. For disk encryption, what you can do is you can ensure at least that if somebody manages to execute code on your system, that after everything is booted, they don't get access to that specific disk encryption key. So you can simply tell the TPM to bind to a certain set of PCR registers, and you make sure that after your disk is mounted, your root disk, for example, is mounted, you make it produce a new measurement which changes the hash of that respective PCR, and then the TPM will not unlock that key unless you reboot your system, because you cannot get the PCR back to the old hash without rebooting everything. Yeah, a bunch of additional measures which you can use and should use is, I mean, they're pretty common if we talk about embedded security. It's you limit the privileges of your process, implement proper file system permissions, so don't run everything as root, obviously. You add additional measures like SE Linux, AppArmor. IMA EVM is also something which helps with runtime integrity. I mean, it's designed for that. And you can also try to limit the blast radius, right? If somebody manages to do that with their device, then it should hopefully only give them access to their device, or let them do stuff with their device and not immediately break all other devices which you sell. So unique keys per device or per small group of devices is often a good idea. Yeah, but let's go on the other end of things. I mean, direct physical attacks. As I mentioned before, on an embedded device, your attacker is potentially the one who buys your product. So they will have infinite amount with the device. So they can do physical tampering and everything they want with that device. The physical chip itself, there's a bunch of things which you can do, tampering, you can look at side channel attacks of all kinds, you can try fault injection and everything like that. The measures against it depend on the individual chip. I mean, it really depends on what the vendor of that TPM implemented in terms of protections, and it's often quite limited. I mean, there's stuff like special coating on the chip, which makes it harder to add probes or to fault injection. There's tamper evidence, which you then, in after the fact that somebody tampered with it, you can see, but it doesn't help you much if the device is in the customer's hand and you will, as vendor, will never see that device again. So it's oftentimes it's a bunch of compliance theater, which does not really help much. But you can also have a look at FIPS 142 or the new one, the 3, which is basically the same as the ISO 19790, because they define certain security levels in terms of physical security also. And you can see or talk to your vendor about what level your chip actually protects you against. I've seen chips which basically have level 2 out of 4, I think, which is really not much. Yeah, but there are easier ways to tamper with the TPM and extract secrets, because there's which is quite prominent with TPMs, is bus snooping. You can simply listen on the bus between the TPM and your CPU and read everything which goes on those lines. And if it sounds much harder than it actually is, because, I mean, as you can see from that post there, which is also, I think, quite old. Yeah, it's from 2023. You don't need much to do that. Ideally, you need access to the bus lines and some way to access them. There's, however, mitigations on the TPM side for that. You can do encrypted and authenticated sessions. They use some HMAC construct, which then makes sure that the certain parameters of your TPM messages and also responses from the TPM are encrypted. And they're also authenticated. So that part really helps, and it's important to use that, but not all clients do. There's a long story of Windows BitLocker not doing that. But I think in the meantime, or at least now, most of those things are mitigated. But if you implement that on your own and you do some custom stuff with the TPM, that's important to remember. Since we were talking about systemd and it's the mcrypt integration, that does that already. So the systemd guys actually do take care of that. If we extend that a bit further, we can, instead of just listening on that bus, we can also send messages or interact with the bus. So we can try to launch man-in-the-middle attacks and act as a TPM towards the CPU, and then try to intercept messages and decrypt messages in that way. Because initially, especially to ensure trust with the TPM, the CPU needs to first talk to the TPM and say, how are you, or who are you? So who are you, and give me your certificate, EK certificates or endorsement key certificate. Yeah, but in that case also, as I said, encrypted and authenticated sessions help you mitigate that, but there's one thing left which you still can do, and that's as an active interposer, you can still always pull the TPM reset line. You can just reset the TPM, and then it will basically keep most of its state, but it will reset the PCR registers, which is what the basis of your measured boot. So in the end, if you have a key which is sealed to a set of PCR values, an attacker can simply pull the reset line, and then they send the TPM new measurements, which will reproduce a valid state, and which will then enable them to unlock the key again, even if they tampered with your software. There is James Bottomley did a bunch of work on that, and I think it's in 6.10 which got a bunch of that upstreamed. He has a great talk on FOSDEM this year where he talks about exactly that. The kernel has now some kind of support for that, but it's two-part. It needs the kernel and it needs user space to do that. And from what I know, the kernel side is there now, but the user space side is still, at least besides some tooling from James I've seen, there's not much there yet. Yeah, it's more complicated than it now sounds, and just go listen to James's talk. You will get confused as I did, and then you have to listen to the talk again, and it gets better. Okay. Yeah, there's also hardware flaws and firmware flaws with TPMs, right? It's the thing is running software. And the hardware is also not invulnerable to flaws. With TPM firmware, you might want to consider as a vendor using a TPM, you have to ship updates through your custom update mechanism, because Microsoft is not going to do it for you. Yeah, and this happened before. I mean, there's in 2019, there has been one paper which they published an attack on ST microchips, which have had some flaw in their firmware. I'm not sure, but I think it was might have been RSA or something with elliptic curve. I don't remember the details. On the hardware side, there's also problems which you can have, and there have been problems. I mean, Infineon had pretty prominently a bunch of million chips which had like an RSA vulnerability. The best thing you can do there is replace the chip. In order to somewhat harden your system, you should, as I said, consider hardening everything else as well, and reduce the blast radius. Yeah, I talked about software TPMs a bit before. The cool thing about software-based TPMs, especially FTPMs, they remove the whole bus snooping attack vector, because you're basically emulating a TPM. There's no bus in between that because it's running on your CPU. But they still can be vulnerable to a bunch of other side channel and similar attacks. So timing leaks and everything like that is still an issue. And there have been issues. I think it's with AMD CPUs or AMD FTPMs, which had the fault TPM vulnerability. It also adds a bunch more things you need to maintain, right? If you use an FTPM which is running in Opti as a trusted application, which is within your trust zone, you have to now maintain Opti. You have to now maintain a trusted application. I mean, most of the time you just have to make sure to keep that updated, but it's still a lot more attack surface which you're adding. Yeah, with trust zones, there also have been vulnerabilities in the past. The trust zones are not like a silver bullet. They can have flaws as well. I've linked one of them here. And with Opti, Opti itself runs within a trust zone, but it also needs a secure storage layer. So it's like a chicken and egg problem a little bit. But Opti has like support for secure storage to that extent which it needs it. It could use, for example, can use eMMC RPMB, but that you have to make sure to configure that correctly and, for example, not include hardcode your key within that. Yeah, I mean, that's almost it. So what are the alternatives we're having for TPMs? I mean, you can also always look into a vendor-specific solution depending on your system on chip, which you might have. I mean, NXP COM is pretty popular. It supports a bunch of stuff like that. It also is a bit faster, like it as a TPM, so you can use it to do the crypto. You can offload the crypto into it, so it's a nice feature, nice to have, and might be also the bus snooping stuff is limited by that. You can think about custom trust zone-based solutions, but to be honest, I think the Opti part is pretty straightforward and better to use than implementing your own stuff. And there's dedicated chips which are not TPMs, but which do more than a TPM does, which you can use. But that's, I think most of the time, it's a bit of a cost thing. Yeah, and hardware security modules, more generic, are also a way to solve that. To sum it up, I mean, using TPMs on embedded systems is definitely an option if you want to go that route. You can use, I mean, really the upshot is you can use a bunch of existing features which are there in, let's say, systemd and everything around it. And that's quite nice because you don't have to reinvent the wheel. You do, however, have to consider the threat model, which does shift in certain areas. And the TPM alone, that's the important part here, does not solve everything for you. You have to do additional stuff. You have to think of what else you have to handle yourself. And you have to implement. OK. With that, that's it. Questions, feedback, always welcome. Yeah.
If I have secure boot and nobody stole my private key, what would measured boot protect me against?
Yeah. If you have secure boot, measured boot will give you the added advantage of being able to do like remote attestation. If you don't need that, that's fine. If you want to seal your key within a TPM to PCR values, which actually makes sense to do, because then you can have a specific point, as I said, with this disk encryption, systemd supports it. You can have your system boot up to your initial RAM disk, and the PCR values have to match for that key to be unlocked. And after that, you change the PCR values, produce new measurements, and then the TPM will lock down, and it will not give you access to that key ever again until you reboot. That will give you, I mean, in the end, will give you measured boot in that case.
It also protects from rollback attacks.
Yes, that's true. Yeah. If you have like vulnerable software and you ship out an update and people roll back to an old version, which is vulnerable. Yeah. It will give you the ability to protect against that because you can reseal your key to new PCR values for that updated version. And the TPM will not unlock with the old software ever again. Yeah.
One question. Some, if not most, vendors do not support the initial encryption of the first stage bootloaders. And then you can just read the measures that will be sent to the TPM from the eMMC. Is there like a better option for this? Or?
You mean like the first step from your boot ROM to your bootloader?
For example, if I cannot encrypt U-boot and U-boot sends measures to the TPM.
Yeah, I mean, you probably don't need to encrypt that. You need to verify that, right? So you need to sign it. If your system on chip does not support that, you're.
I mean, even though the communication between my chip and the TPM is encrypted, if what I'm sending to the TPM is just plain text in the eMMC, does this really help me?
No, I mean, the stuff you're sending to the TPM, that's what I mentioned. You have to use TPM authenticated and encrypted sessions. And those is a thing between you, the CPU, and the TPM, which you have to set up. And then it's not plain text what you're sending.
But it's plain text in code that I'm actually flashing on the system. No?
I don't get the question really.
You're verifying the firmware. That is, you're verifying the U-boot firmware that's doing the session. That firmware is setting up the encrypted session and sending values. So the fact that you know what value it's sending isn't the threat. Right?
Based on what is the
session encryption.
Yeah, you
That's not authenticated. That's not authenticated.
you also do authentication. I mean, the way this works, to set up the encrypted and authenticated session with the TPM, you first send the TPM some secret, which is encrypted to the endorsement key, for example, or some key within the TPM. And then only the TPM can decrypt that. And via that, you agree on a shared secret between you both. And via that, you have encrypted and authentication key on both ends. Why are you shaking your head? What's unclear?
Because you're only authenticating that you talk to the right TPM.
Yes.
The TPM has no way of authenticating
You.
the system sending it if it's not encrypted.
That is true. The CPU.
You can mimic POS.
Yes. You can. The TPM has no means of validating anything besides the part it gets, right? That's what I meant with reset attacks. Somebody can reset the TPM, reset the PCR registers, and simply send the same measurements as your system usually does.
But wouldn't you connect it to the counter? Because if I understood correctly, for the PCR, you also have the reset counter.
Sorry, it's a bit hard to hear.
I should have stood up before. Wouldn't you use a counter? There's a reset counter for PCR. So you would look at your PCR, but also...
I mean, PCR is reset, right? The value in the PCR.
There's a counter for it, which allows you to see that something has changed. So this is the last time you looked at it.
As far as I'm aware, with a reset that you don't get that.
Okay, so it's only for reboot then?
Yeah, from what I know, yes. I mean that's the whole point of this kind of reset attacks, right? You basically mimic what happens during a reboot.
Okay, my understanding was that whenever you change the PCR, you reset it, it would increase the counter, which means you get that something has been modified the last time, but I might be completely...
As far as I'm aware, no, because there's a reason why kernel 6.10 added the whole thing with null key hierarchy. Yeah.
Speaking of the null key hierarchy, there is a patch set from Google 10 days ago that disables HMAC session stuff because it's inherently not secure.
Oh, really? I haven't seen that patch set yet,
Yes.
but I'm curious what James is going to say about that.
Okay.
To be honest, I cannot tell you because I haven't seen the patch set yet.
I'm wondering if one shouldn't just recommend using FTPM all the way because DTPM have inherent issues.
I mean, yeah, the bus snooping stuff is pretty prominent right now, especially with Windows having issues for years now. FTPM will save you that side. It will bring, as I said, it will bring a bunch of new stuff to maintain. If you already have Opti running, okay, right, that's just a TA which you have in addition to that. But yes, it will save a part of that. Any more questions? Yeah.
So is an HSM a TPM as a cloud service, or is it something else?
It's more, but that's a whole another discussion we can have there with HSMs. We can talk afterwards.